So here we go on this Unit 7, Week 5, Lecture 10, Part 1. Now the activity that you all did in class where you observed water, ethanol, and hexane, excuse me, in that activity you were asked to articulate a model at the end to explain, why the different liquids had the different properties. And this lecture will explain what scientists have agreed as the model to explain differences in physical properties using the concept of intermolecular forces. So our model that we use to explain is called intermolecular forces. So that's what we're going to be talking about today. Okay, now when we discuss intermolecular forces, we have to be careful and get it straight in our heads, the difference between intramolecular forces versus intermolecular forces. Okay, it's very important to get that clear. The intramolecular forces are the forces that hold atoms together, inside the molecule. We call those bonds, in particular covalent bonds. Intermolecular forces are the forces holding discrete molecules or ions together. Okay, so those are the forces holding discrete molecules or ions together in a condensed phase as a solid or a liquid. That's what condensed phase means. Okay, and so we have to be really careful when we look at an ionic compound versus a covalent compound to keep the difference between, are we talking about intra or inter? Now, as it turns out, we call the attractive force between ions in an ionic compound, we call those ionic bonds. But what we're going to come to realize, since the sodium and the chloride ions are discrete, and if you melt this, or if you dissolve this in something, or if you put it into a gas phase, you're going to end up with discrete sodium ions and chloride anions anytime you separate the crystalline structure. And so that's actually what we would consider an very, very strong intermolecular force. But it's so strong, it's when we introduce this concept to people, we introduce it as a bond, and it bonds, as we'll see, electrostatic attraction. So this is really a very, very strong type of intermolecular force. We use it loosely because we know that these aren't molecules, that's inter between the discrete ions. This might look kind of complicated, but this is, the red is oxygen and the white is hydrogen. And what you see here is ice. And so in this picture, we have intermolecular forces and intramolecular forces holding the individuals together. So let me see, here's an individual water molecule, and that would be an intramolecular force, and this would be an intermolecular force. So intra versus inter. So we're going to spend some time across this lecture, Part 1 and Part 2, nailing down this concept to understand the difference between intra and inter. Okay, here is a better picture of what you were just looking at with the water situation. And in this case, the blue are the covalent bonds, so that would be the intra. And in the case of water, there's a special name for the attractive force between the individual discrete molecules. This is a discrete molecule. This is a discrete molecule. And this special force that holds these discrete molecules together in condensed phase is called hydrogen bonds. Okay, but even though this is using the word bond, this is what we would consider an intermolecular force, and this is intra. Okay, so we need to take a look at this and see, make sure that whenever we look at a situation where we have molecules in a condensed phase, we can distinguish between intra and inter molecular forces, right? Let me show you. Here's another example. These are methane molecules, and these are water molecules. And so if you're looking at this picture, the question I would ask you is can you draw the inter versus intramolecular bonds? Can you look at these images and decide what's inter and intra, or can you draw them? And so in this case, this is the water molecule. This is the inter intra, because it's within the discrete molecule, and then there would be an attractive force between these molecules. And let me draw another molecule of water. Okay, and so the attractive forces are going to be between the individual discrete molecules, inter forces. In methane, you'll see that this is, if you think about methane, methane is a gas normally at room temperature and pressure. Water is a liquid at room temperature and pressure. Okay, and so what that's going to lead me to understand is that, you know, what holds something as a, and the size is very similar. This is molecular weight 16. This is a molecular weight of 18. So the mass of these two molecules is very, very similar. But the water is a liquid at room temperature and pressure, and methane is a gas. And that's because in the case of water, water is a polar molecule. So our electron cloud is unevenly distributed. So the water molecule itself has a negative end and a positive end. Whereas in the methane, the charge distribution is equally distributed. We can't say this end is positive, this end is negative. There's no polarity associated with it. So therefore, the intermolecular forces here are so weak that if it's in the gas phase, we'd say there's no intermolecular forces, okay? So the intermolecular forces exist only in the condensed phases of material. So we need to understand, we know that we can liquefy and force methane to become condensed. We know, you know, water, we can make it into a gas if we heat it up. So we want to try to understand, how does all of this work to be in a gas phase or a liquid phase.